Hello my friends, welcome to my tutorial. In this tutorial we will design and simulate a bit more complicated gas target, a beveled nozzle. So the complication comes from the required geometry and the meshing, which is a bit different. I will show you what we have to do to properly mesh and run the simulation. To design the nozzle or to draw the nozzle, we will use the part of the drawing that we made in the 2D axisymmetric geometry. If you haven't watched the video, just please watch it. But also you can draw it. It's not very complicated. So in the first step we will just duplicate the first case, so this one, and we will modify it accordingly. All right, let's give it a name. So let's call it of course it's 3D. Since we don't have any symmetry, it has to be 3D. And besides this one, of course, in the setup, so just to avoid any mistake, let's just reset it. So we will have to define all the parameters again. So let's open the geometry. So now we start the design modeler, and you remember, I hope, this geometry. We don't need the surface, so we can delete it. And click on XY plane, right click, look out, and we have to delete these boundaries, and we will just add here an edge. So to delete, just click on sketch and modify, and we can use cut. So if you keep pressed right click, then you can choose multiple axes, and also this one we need to delete it because we need to redraw it, and just press delete. And now let's go back to sketching, draw line, and from this point to the axis, and from here to here. That's it. And now we will do a rotation around one axis to generate the geometry that we need. So for that one, revolve. We choose the geometry is sketch and axis. Now if you click on these ones, you can see which one it is. So if you rotate this one, of course it's not this one, it has to be this axis. So it should be, oops. Apply and generate. And now this is our nozzle. We don't have the region outside, so after we finish generating the beveled nozzle, we need to create that region outside. So right now, let's click on XY plane and press here, generate a new plane. So the type from plane and transform. So this will permit you to make changes to the coordinates. So click on transform 1 and offset X. So I want to move it from here, from where we have the 0 axis, to move it right here. So for this you need to measure the distance from here to here. So you remember, you just use tools and analysis tools. From the previous I don't have it here anymore, so I need to measure it again. So we can use generate, it doesn't really matter now. Tools and analysis tools, distance finder, edge, this one, apply, and this one, apply. So it's 17196, so write it down. So we will need this distance also when we create the region outside. You will see why. All right, and now let's go back to plane 4, right click on it because we need to modify it, and offset X. So now we write down 7.196, and if you press generate, you can see it now, it's moved right here. And now we need to tilt this plane 45 degrees. So you will see in a short time why we are doing this. So again, right click, edit selections, and we can transform, and we go rotate about, we can have about X, Y, Z. So rotate about Y and 45 degrees. And I think I chose the wrong axis. No. So you'll see now it's going like this. So this is the plane that we will use to cut the nozzle. Of course, if you don't, so right now it's exactly in the middle. If you don't want exactly in the middle, you make the third transformation, which is offset. So in this case it has to be offset, so this is X, Y and Z. So you can choose this one and how much you want, -1, -2, so you can go in one direction or the other. But right now we don't need this one. So we want to cut a section exactly through the middle at 45 degrees. So generate. This is the plane, and now we choose plane and create and slice. And slice by plane, so you have multiple options. For instance, if you want slice of faces, surface, edges, and so on. We can explore what choices you have with each option. So in this case, just slice by plane, and we chose plane 4. And if you press generate, now we will have two parts. So it's one part is the section that we cut, and the second part is the rest of the nozzle. So this section, we don't need it anymore, so right click on it and suppress. So it will disappear. This is the nozzle. You can see it here. Something like this. All right. Now it's now let's generate the surface, the outlet. So it will be a cylindrical region that will start somewhere here and it will go around. So for that one, create primitives cylinder, and in this case, since it's oriented in the X direction, then we will need to define this. So it will be let's say 6 millimeters about, and this is 0, and the radius we want So the nozzle is about 2 millimeters diameter, so to have enough region outside to see the profile properly, let's say we will put 4. So the entire cylinder will be 8 millimeters. We'll see if it's too big. And now we need to translate this one. So let's try X, translate it to 16.196. All right. So before pressing generated, let's check if it's the right. So we want slightly below this region. So it looks quite okay, and we press generate. Now if you press on this one and hide face, we can see inside. It looks right. All right. So drawing the nozzle is pretty much done. Close. Ctrl S to save the project. Do this periodically just to avoid any headaches. Double click on mesh and the meshing program will start. Now the geometry will be updated. Some warnings because we had a different geometry before. So here the name selections are not valid anymore. We need to check them to choose them again. Alrighty. So center line, we don't have it anymore. So we delete it. And pressure inlet, we need to select it. Let's rotate the geometry like this. Choose surface, this surface, apply, and we have pressure inlet, pressure outlet again, geometry, and we select this one and this one. So if you press Control, then you can select multiple surfaces and rotate. Again, press Control, and we have 3 of these, 3 surfaces. Everything is fine. And we will do something else just for to be sure that we will not do any mistake. So right click on this one and hide. Okay, let's rotate a little bit. Okay, why didn't it disappear? So okay, so and now we choose this one and this one, this, and create name selection, and let's call it wall. So if you hide face, okay, so here is an error, it doesn't hide, but it doesn't matter, is okay. So when I select this one, I can see the shape here. That means also the region inside is considered as wall and not ignored and considered as an interior. So we have to make sure that we have this chosen properly. All right. Now we have, if you remember from the 3D case, we had face meshing and insert method. Where is it? Okay. So we had method and geometry, and from the 3D case, you remember we chose multi-zone. So this is with hexa cells. But now if we are trying to do the same, so mesh, and here is one. If you are trying to mesh, we'll discover that actually it doesn't work. It will give an error. That's because the geometry is too complicated to be able to mesh with this this kind of mesh. So let's update. And now it's starting to mesh, and update failed, so it couldn't mesh. In this case, we don't really have other option. Okay, so we forgot to do something. So close the program. But anyway, even without this this choice, it will not mesh it. So this is a very important thing. If you have multiple regions like we have now, so we have the nozzle and we have the cylinder. It's good I did this mistake, because it will be very important when you are drawing multiple regions or multiple sections. Sometimes it's necessary to do that, otherwise you cannot mesh it. So for instance, this nozzle, you can draw just this cylinder, this, after that this conical part, this cylinder, and this conical part, and this cylinder. And if you are drawing like this, then when you mesh it, you can mesh each section separately, but to be able to have what is called conformal mesh, so you have continuity between each section, you need to tell the program that these two are part from the same mesh or from the same geometry. So right click, you choose both of them with right control, and right click on this and form new part. So these two, the program knows now they are the same part. So we can close it now. Again, we start the program. All right. Okay, it will update. Okay. And now when you click on mesh again, if you press update, it's trying to mesh, and most probably it will fail. And also it will fail because I didn't choose the entire so if you check here, instead of meshing with just hex, it uses pyramidal shapes and tetrahedral shapes, and we don't want that. We need only hex. For this kind of simulations, you must always have hex. So it doesn't really work. So instead of multi-zone, we will choose what is called Cartesian. This is not the best mesh that you could have. It's a bit harder to control during the simulation, so it's much easier to diverge because the quality of the mesh is not that good, and you need many more cells to fit the geometry. But we don't really have a choice, so again, right click, update. So the element size, so if you are not happy with the number of cells, if it's too much or not enough, you can change this number. This is the most straightforward way to change the mesh size. So we see here we have only hex. We are happy with this. And let's see statistics. So it's almost 1 million cells. It's fair. Normally I would prefer to have 2-3 million of cells, but of course if you'll use Ansys Student, that is limited in number of cells, so you can have only 1 million cells. It's okay, you'll get quite a good result, but to be sure that your result is accurate, normally you have to do what is called mesh independence. So what does it mean? You will increase the mesh, the number of cells in the mesh. So let's say 100,000, 500,000, 1 million, 2 million, and the solution shouldn't change as you increase the number of cells. So that means the solution is mesh independent. But from my experience, this is quite okay number of cells. So this is meshed. We named the boundaries, and we are pretty much done. We close the mesh program, the meshing program. Alrighty, and now let's start. Okay, wait, it's closed, and we start the setup and double precision, and here the number of processes, the parallel processes that you want to start at the same time. Remember, Ansys Student, only 4 processes, is limited by the license since it's free. Otherwise, you can choose as many as you want, or as many as cores as you have. So I will choose 62 because I have 64 cores. Start. And now the geometry is imported. Now there is a bug in the program. So sometimes everything seems to be fine. So the mesh is checked. It seems to be the meshing to be successful. But when you're trying to import here, you'll have a weird error, a Cortex something error. So that is most of the time a problem with the mesh. So you have to go back and remesh it. Now this is the geometry. As you can see, this is the outlet. It's always marked like this with those errors, and here is the inlet. If you zoom on that region, you will see some arrows pointing inside. That means it's the inlet. And now let's start the scale. Put it in millimeters because it's easier to visualize the data and everything else. Alrighty, check. So settings. Okay, no error, everything is fine. Report quality. If you know the meaning of this, so if you don't know, just check the help, the documentation for this Ansys Fluent, and you'll see the definition of all of this. Units, and here for density, new, I always use so here is a factor which I already know it because I calculated. So the units in I like to use these units 10 to 19 atoms per cubic centimeter. So this factor that I am writing here, you calculate it using ideal gas law. So you just transform from pressure to densities. It's not a big deal. I will not explain it here. If you don't really know it and you want to save time, just use ChatGPT. Yeah, it's not ideal, but whatever works for you. So I have this, so whatever result I have there is multiplied by 10 to 19 atoms per cubic centimeter. It's just, it's a better unit for laser Wakefield accelerators, or at least for the profiles that we use in Wakefield accelerators. Okay, close. We choose density based, if you remember from the previous settings, from the previous cases that or the previous tutorials. Energy equation, this one viscous, we don't change anything, we keep it by default, they work the best. We finish with models, materials, create edit, Fluent database, and we go to helium. In Wakefield accelerators, we use, in experiments, we use helium or hydrogen, or sometimes doped with small quantities, 3% of nitrogen, neon, and so on. But the main gas is helium or hydrogen. Copy, close, close, and we go to fluid. And instead of constant here, ideal gas, change create. Even if it's ideal gas, the rest of the gas parameters or the gas properties are real ones. So don't get confused by this, because by definition, in an ideal gas, the difference between gases is just if it's monatomic or diatomic, but the rest it doesn't really matter. But in this case, we take the real properties of the gas. Close. All right. Now here, solid is aluminium by default. We don't care because we ignore the walls. The walls are infinitely thin and adiabatic, so there is no heat transfer between the gas and the walls. All right, and we go to, so we have to do something else. So cell zone conditions, double click on it, operating conditions 0, because it's surrounded by vacuum, so that is your reference. And here edit, and by default, even if we imported helium, we need to define it here if you want to use helium, so be careful about this one. Don't forget to choose helium. Nothing else we will change. Apply, close. And now the inlet, pressure inlet, let's say 30 bar, so that means almost 3 million Pascal. And here a slightly lower pressure, it doesn't matter, it just has to be just lower to move the flow. Again, if you don't know what I am choosing here and why I'm choosing this, just press help and you will it will take you to Ansys Fluent documentation. Turbulent intensity 5%, and this one 1. Apply. And if you have a certain temperature that you want to define there, you can define it here. I use the room temperature because the gas is at room temperature, so it makes sense. Outlet, pressure outlet, this is the vacuum pressure, so it's about 0.01. Again, hydraulic diameter 5, and here it doesn't really matter. it's the outlet and it's very far away. All right, close. And the wall, now here you I don't change anything, but if you want to define the roughness of the wall, you can do it here if you know what you are doing. So you can define for instance, depending how the nozzle is manufactured, mechanical or 3D printing or so on, you know the roughness or close the roughness of the wall, so you can define it here and take into consideration. But keep in mind that if the mesh is not fine enough so that you can see this roughness, so if you have a roughness of, let's say, 5 microns, if the mesh cells are much bigger than this size, it's like you don't have any roughness, so it's not seen by the simulation. So be careful, you have to have a very, very fine mesh to take into account the roughness. And you have all sorts of definitions here. Press help, takes you to documentation, and you'll see how to choose this or why you should choose this. Again, if you have walls and you want to take into consideration the heat transfer between the gas and the walls, is done here. Again, you need to know what you are doing, so press help if you don't know, and you will see how to choose these values and how they are defined and so on. You have all the theory behind this section or behind these options. We will not choose anything here. The walls are adiabatic. Apply, close, and we finish with this one. And the rest of the options here, we don't care. Make sure we have second order upwind, which is fine enough. The solution is fine enough for us. If you have first order upwind, it's not okay. Make sure second order upwind for all these three. At controls, we don't change anything. The most important here is the current number. If the solution will diverge, you have to decrease it, but we will discuss in a future video how to when it's proper to change this one and what better options you have than changing this one. Don't worry about current number right now. We go to monitor, so we need to monitor the residual. I like to choose a smaller value. I don't like the default value. Sometimes it reaches the value that I define here, so 10 to minus 5, sometimes not. So depends on the simulation, depends on the conditions, so don't worry too much about this one. It doesn't have to necessarily reach this value to converge. There are other criteria. If you watched my previous videos or tutorials, I already discussed this. Okay, and report files, we don't care about this one right now. So report plots, this is what we are interested, and we go to new surface report, and we choose, let's say, facet maximum, and the variable is density, so we will monitor the density at the outlet. This is very important. It's one of the criterion for convergence. So we monitor the density at the outlet, and when it doesn't change anymore in all the points, then one of the criterion for convergence is reached. So okay, and now we need to add it here so that it will plot. Okay, and close. Alrighty, now we need to initialize. We don't change anything here, we use hybrid initialization. Initialize. Okay, so it complains that the convergence criteria according to what it should be is not reached. So that means we will have a problem with convergence. We have way around this, so we don't really have to worry about this warning. Most of the time this is a problem with the mesh. So the mesh, the number of cells in the mesh must be increased. Let's not worry about this one right now. And calculation, so auto save, let's say every 1000 iterations, edit, yeah, let's keep all of them, it doesn't really matter now, and run calculation, check case, no recommendation, so that means most probably we haven't forgotten anything. Number of iteration, put whatever is there, 1 million. And what we have to do now is create some line outs above the nozzle, so that after we finish the simulation we can use to check the density profile. So if you go to plots, setup, and we go to new surface, line rake. So you remember we had so the outlet started at 17.196, so we will have here 17.196, and so actually 1 millimeter above the nozzle, so it should be 18.196 and 18.196. Here is from -4 to 4, if I remember well. So this is the diameter of this big cylinder, and let's call it X1. Create, and 2 millimeters. Oops. 19, not 13, and X2, create, and on X3, so 3 millimeter above the nozzle, that's 20, and I will not make more. You can make more if you want to see the profile, how it changes. Close, and if you choose these ones and choose density, plot, of course we need to choose the proper so if it's deactivated it plots like this, so we need like this. Let's say plot, and this is the density profile calculated with these initial values. Of course it's not correct. Okay, close and run calculation, and if you press calculate, now it starts to run, and if we wait for a while, because of that error that we had, it's very possible that it will diverge. So let's see a couple of hundreds of iterations if that will happen. So the Ansys Fluent will reduce the current number automatically, or what is called a time step, so that if it detects a divergence, the time step or the current number is reduced to avoid divergence. But sometimes it cannot cope with the accumulated numerical errors, so it will diverge very, very fast, and you will have to do something else to get convergence. But it doesn't seem to be a problem now. Let's see. So in case you don't know the divergence, it's easy to spot. So these curves, they start to go up very fast, and they reach very high values. But right now the Ansys Fluent is capable to correct for these errors. So you see it's going up and down, and here it changes time step. So this is a steady simulation. So that means the time step is not fixed, and it's adjusted so that the flow reaches what is called the steady regime. So it's increased, decreased depending on the flow. If the flow is too fast, then the time step is reduced. If it's more less turbulent, then the time step is increased. And steady, of course, is reached when the density doesn't change anymore everywhere in the geometry or in the fluid domain. Okay, everything's to be fine. So by now it should have diverged if that was the problem. So if you stop it and plot XY plot, so you already start to see here some weird profile. So this is very close to the exit of the nozzle. We see here a bump. So that tells us that the profile will start to be will not be any more flat top profile like in the other cases, but it will start to do some shape here. So in this case, from my experience, I already run this kind of simulations. So it will be the profile will be a flat top followed by a long ramp, and that will change. The flat top might disappear if you choose a different position for the bevel. So it will be just a very fast up ramp followed by a very long down ramp. And let's try to see if we can plot graphics and contours. So yeah, before this one, let's create some isosurfaces. So isosurface, mesh, and let's say, so x coordinate, so it will go through 0, and y coordinate, create, and the z coordinate, create. All right. And now if you plot these ones and density, so yeah, I just chose some random, so of course we cannot see anything. So this is exactly through the middle of the nozzle. And if you zoom, and now if so let's choose color map and log scale and 20 colors. We can see now the density profile. Of course, it doesn't really mean much now because it's at the beginning of the simulation. So we need to let the simulation run until 3 conditions are met. So one condition, residuals, has to be as low as possible and ideally shouldn't change anymore, so it should be a flat line. The next one will be the density at the outlet should not change anymore, so again reaches a plateau and doesn't change anymore. And the most important one is the mass flow rate between the inlet and outlet should be the difference between them should be 1% or even less. So that means the mass is conserved. So the amount of fluid that is going through the inlet is equals the amount of fluid that goes through the outlet. If you have all these three criteria met, the simulation is converged. You can stop it, extract the data. So to extract the data, don't use only this one. So you can have here some of the results. You can extract them, but to extract the data properly, use results. So this is CFD post, and there are the proper tools to extract all the data, sections, cross sections, profiles, and so on. Also, you have the option, if you don't like to use CFD post, or you have MATLAB or whatever you want to use to extract the data, just go to File and Export Solution Data. And now you can choose, for instance, density, and you can choose where you want to have the entire density in every point inside the nozzle, so from the inlet up to the outlet region. So if you press this one, you can choose what kind of format you want for the file, right? And you can export it where you want and analyze it after that with whatever program you want. But from my experience, if you are using CFD post, so this one, this is really nice because you can you have so many tools here that you can use to extract. So it's not only quantitative data but also qualitative data. So you can see streamlines, you can draw streamlines and so on. So this is pretty much the tutorial. I will let the simulation run in case it will start to diverge. If it diverges, then I will prepare another tutorial to show you how to avoid divergence. At some point we will encounter divergence, even if you don't want to. And anyway, I will need to prepare that video to show you how to get rid of divergence and run successfully a simulation, no matter the geometry, no matter the conditions, and so on. So thank you for watching, and see you next time.